sequence. Maybe. There we go. All right. I guess starting with in other words is a very good way to start. So let's go back a slide. Okay. All right. And I think we talked about this one already, and I already said what was the other words on the other slide, but just to give a little continuity. Any questions on anything so far? Okay. Now, this starts, it is a function. What is a function? Let's see. All right. We know that a set of ordered pairs is a way of expressing a function, and we talked about this, and we talked about what the inverse function would be, the one that undoes this one, and that's what it is, a function that undoes that one, and we talked about that, and we talked about the fact that you start with the domain of f, and that's where you find your x, okay? Act on it with the f function, that puts you over in the range of f, which is your values for f of x. And then, if you're going to the inverse function, and you go back this way, you wind up with the same x you had to begin with. And that's what, in other words, okay, when you form the composition of f with f inverse, suppose f of f inverse, okay, or the composition of f inverse with f, you should obtain the identity function. Now remember, most of the time, when you do f of g, and then you do g of f, you get completely different things. Most of the time that's the case. But when the two functions are inverses of each other, then not only do you get the same thing, but you get the same value every time, and that's x. Because the f inverse is undoing f, and then when you undo, this undoes f, and then you do f again, you wind up what you started with. Or f of x gives you a y value, say, and then you undo that with the f inverse, and it takes you back to x again. So this is pretty simple. In this case, your f inverse was x minus 4. When you operate it from the f function, which is x plus 4, you take what's in here, x minus 4, add 4 to it, you wind up with x. Well, minus 4 plus 4 is 0. Well, when you start with f of x inside, that's x plus 4, and then operate it with f minus x, which is x minus 4, you take what's inside here, x plus 4, put it here, subtract 4 from it, you're back at x again. This is a very simple example, and if you feel like you're going around in circles, you are. That's exactly what you are doing on your mapping diagram. Okay? Now, they're doing the very simplest functions now, so that you could almost guess what the answer will be. And that's what they want you to do on this one. Find the inverse of f of x equal 4x. Okay? Now, they haven't told you how to find it. So basically, it means guess. What would you guess the inverse function of multiplying x by 4 might be? Second?
The inverse of multiplying.
Yes? What operation undoes multiplication? Division. So your f inverse, at least a guess, and let's see if we're right. If I can get the pen up. Okay. We'll guess the f inverse of x, this is a guess now, to be x over 4, dividing by 4. Okay? Now it says, then verify that both f of f inverse and f inverse of f, the two composites there, are indeed equal to the identity function. If they both are, these are inverses. Okay? So we'll do the first one. What is f of f inverse of x? Okay. What do you plug in first? Inner. And what was our f inverse? X over 4. Okay, and then you operate on that with the f function. Oh, I don't need that again. Okay, the f function says start with the number 4 and then multiply it by what's inside the parentheses. And that is x over 4, and 4 times x over 4 is indeed x. Yes, we're halfway there. All right, let's do the other way. F inverse of f of x. Okay, well, that would be do with the inner, so leave the outer alone for now. And what's your inner function? F of x? 4x. Okay, perfect. Right there. F of x is 4x. Okay? Now, what does the inverse function tell you to do? Okay, it's take whatever's inside here and divide it by 4. What's inside there is 4x, and divide it by 4, and ding, 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 you got an x. Yes. So you have verified that your guess was right. The inverse function of 4x would be x over 4. And you verified it. Both ways. You got the identity function both ways. Okay. And remember, when you plot these things, you get the identity, they reflect across the identity function. So, maybe not too awfully surprising. There is a checkpoint here. Please try to do that soon after class as you can. All right. Oh, let's see how they did it. Let me clear the ink and see how they did it. Since the function f multiplies each input by 4, to undo that function, you need to divide each input by 4. So your intuition was pretty good, okay? That the inverse function of f of x equal 4x might be the inverse function of fx being x over 4. Let's verify it and see if it's true. We'll first do f of f inverse. Let f inverse is x over 4, so we're going to operate with the f function onto x over 4. But the f function was multiply whatever's inside the parentheses by 4. So when we do that, 4 times x over 4, sure enough, is x. Okay? It even changed color for you. Okay, that's great. All right. But that only gets you halfway there. Let's verify it the other way, f inverse of f, and f, of course, being 4x. And the f inverse function takes whatever's inside the parentheses, x, okay, in this case 4x, and divides it by 4. So we take 4x over 4, and sure enough, right at the bottom of the page, that becomes 4x as well. So we have verified both f inverse and f inverse of f are the identity function, so this indeed was the inverse function. If either of those had turned out anything else, that wasn't the inverse function. All right, any questions? And again, there's a checkpoint at the bottom. All right, here's the definition of inverse functions. Pretty important things to keep in mind. Let f and g be any two functions such that f of g of x happens to be x for every x in the domain of g. And at the same time, g of f of x is equal to x for every x in the domain of f. That's where you're starting. Now realize these can have different domains. So they may operate on different things, but within that constraint, that every element x within the domain of g for the first one, f for the second one, you always are going to get x as the answer. Under these conditions, f is said to be the inverse function of f. I mean, g is said to be the inverse function of f. The function g is denoted by f inverse. Okay, that's not f. Well, you can say f to the minus 1. Don't confuse that with reciprocal. Call it f inverse, so you know it's not. So this means f of f inverse is x, and f inverse of f is x, because you just replace the g's with f inverse. So the domain of f must be equal to the range of f inverse. The domain of f must be the range of this, because you operate, the input here is the domain of f inverse. The output here is the range of f inverse, and that must be the domain of f, because that's what f is operating. Okay? And the range of f, right here, when the domain is what you put in, the range is what comes out, the range of f has to be the domain of f inverse. Okay? So, those must be met. Those conditions must be met. All right, let's see about, all right, do not be confused, okay, I've been saying this all along, but let's hit it again, with the use of a superscripted minus 1 to denote the inverse of the function f. In this text, whenever you see a function raised to the minus 1, that's always an inverse function, never reciprocal. If you see a number raised to the minus 1, reciprocal. If you see a variable raised to the minus 1, reciprocal, but not a function. Okay? Now, if you had an expression like x minus 4 to the minus 1, that's reciprocal. Okay? It's only if you have the symbol for a function, f, g, whatever it happens to be, to the minus 1. If any of you continue to trig, your trig functions, sine to the minus 1 is an inverse function. It is not a 1 over sine. Okay? So any kind of function to the minus 1 is an inverse, not a reciprocal. If the function g is the inverse function of f, then it must also be true the function f to be the inverse function of g. They go hand in glove. You can't have one without the other. For this reason, you can say that functions f and g are inverse functions of each other. Short way of saying it. Okay. Well, they're skipping example 2. They did the easy one. Now they're skipping 2. So let's back up and do 2. Whoops. Let's start right there. All right. This time they give you a function, f of x, and they tell you that is at 5, I can't write, over x minus 2, and they're asking you a question. Which of these two functions, g of x, which is equal to x minus 2 over 5, or h of x, x, yeah, I said it right, I think, and wrote it wrong. Okay, okay, all right. X minus 2 over 5. Say again?
Is that or h times x?
Or, yeah,
Okay.
h of x is equal to 5 over x plus 2. Okay? Here are two different functions. Are either one of these the inverse function of f? There's the question. How do we check and see? Okay, how do you do that? Yes, do a f of g of x, and see what you get. Well, we'll plug in the g first, so that's just going to be f of, the g function is x minus 2 over 5. Okay, now the f function says you start with the number 5, divide it by what's inside the parentheses, the x there, but in this case it's x minus 2 over 5, and then subtract 2 from that. Sort of a mess, huh? Now this is what, yeah, in most algebra texts they call a complex fraction, because it has a fraction within a fraction. Okay, I don't like that term because most of the time in mathematics, complex denotes an imaginary component somewhere. We don't have any imaginary components. So I like to call them complicated fractions, but most people say, well, all fractions are complicated. So that's not a good term either. So we'll call it a complex fraction. Now, how I recommend that you simplify a complex fraction is find the least common denominator of all the denominators, and most the numerator and denominator. Well, we only have one. That's a 5. Okay, once you found that least common denominator, multiply the numerator and denominator by that denominator. Okay? So we're going to multiply the numerator times 5 and the denominator times 5. And why can we get away with that? What's 5 over 5? It's 1. And you can multiply by 1 anytime you want to. So the numerator becomes 25. Now the denominator, you're multiplying this 5 times that whole thing. Well, in the first term, it cancels out the 5, and you're left with it x minus 2. And in the second term, when you multiply that, you get a minus 10. This is not looking good. Okay, it didn't look too good from the beginning. You got 25 over x minus 12. Any way that's going to be an x? No. So this is not the inverse function, okay? Well, we don't even need to try the other way, because if either one of them didn't work, can't do it. So now let's try the other one. Let's try h of x. So now we'll start with f and do f of h of x, okay? And that would be the f, leave that alone for now, and plug in what h is. That's 5 over x plus 2. Okay? This doesn't look like it's going to be too promising either, does it? Okay, well, what's the F function? The F function starts with the number 5 and divides by whatever's in the parentheses here, which is 5 over x plus 2, and then subtract 2 from that. Right? Got it?
You said this.
The minus sign here is a plus sign there.
For h of x.
Second,
For h of x.
for h of x
It's a
is
plus.
that thing. Is what we're plugging in. Okay, yeah. It's f over x divided by 2 is what h of x is.
Right.
Okay? And this is what we're plugging into the x value
Okay.
here.
Okay.
Okay?
Okay.
So it's 5 over this thing here minus 2. All right. Well, the good news is you can remove the parentheses because they're really not doing anything for you. So let's take those out. And then you notice that minus 2 plus 2 is 0. Oh. Well, now you got 5 over x, which if we wrote it a different way, that'd be 5 divided by 5 over x. And you remember how to do division of fraction? Invert and multiply. That would be 5 times x over 5, which, ding, ding, becomes x. So it looks like that could be the inverse function. But we really need to verify, don't we? We love verifying, don't we? Yeah, not done yet. Okay? So what I'm going to do is erase this one that didn't work, if that's okay. All right, and we'll do the other way, okay, which would then be, because if they are reciprocals of each other, I mean, not reciprocal, if they are inverses of each other, then it must be true that h of f of x must also be x. So let's see if it is. So again, the h function we're going to leave alone for now. We're going to operate on our f function, which is 5 over x minus 2. Okay? Well, the h function says start with the number 5, divide that by whatever's in parentheses here, which would be 5 over x minus 2, right? If my pen would write, okay? Then add to that plus 2, you see? This thing, when I rock my screen, it shorts for a moment, and then comes right back. Okay. Now, did I do that right? The h function starts with 5 over whatever is inside here, and then adds 2 to that. Right? Got it? All right, I think because please excuse my dear Aunt Sally, we got to do our division before we do our addition, all right? So let's do that. And that's something similar to what we did before. Let's go over here to our scratch side, and that would be 5 divided by 5 over x minus 2, right? It'll come back. Yeah, there it comes. Okay? And how do we do that? Change that? How do we divide that? 5 times x minus 2 over 5, multiplied by the reciprocal. Absolutely right. The 5s now cancel out as little things keep trying to sneak in here. And that leaves us at x minus 2. So this thing is x minus 2 plus 2 is, get out of there, that's equal to x. So sure enough, both h of f of x is x, and f of h of x is x. Therefore, F and H are reciprocals of each other, not G. G was the, I'm sorry, I said it wrong. H, F, and X are the inverses of each other. G was a reciprocal. That's not the same. Okay, good deal. If I can ever get out of here alive. Okay. There is a checkpoint at the bottom of that page. And remember, all the checkpoints, if you get stuck on them, they have an audio-video solution at larsonprecalculus.com. In both English and Spanish, by the way. If you don't want to know what. Okay, never mind. Okay, so let's move on to graphs of inverse functions. Okay? Now, if you remember back that earlier example we did right at the very beginning, it started with the ordered pairs. If you think a little bit further back from there, you remember that how you get the inverse function is just reversing the ordered pairs, right? Okay. Now, if the ordered pair represents the x value first, the y value next. So, you get that. Well, if you reverse the order, then what was y becomes your x. So you do that first, and then do what was the x becomes the y here. So the point that was here becomes over here. Okay? So, that should lead to something. So let's see what that leads to. The graphs of function f and its inverse function f inverse are related to each other. They should be. They're coming from the same source. If the point AB lies on the graph of f, then we know that the point BA must lie on the graph of f inverse. That's how we define them from the graph. And vice versa. Okay? This means that the graph of f inverse is a reflection of the graph of f across that good old identity function. Okay? Here's a function. We don't know what it is. We just know f of x looks something like this. It starts down here, goes up here, runs to here, goes on up. Well, f inverse, whatever your a, b was here, your BA must be here. Okay? So this function, where this is coming from a very steep slope, this comes from a very shallow slope. And by the way, anytime they have the same value, that's going to be on the identity function y is equal to xy. Okay? And because there, you exchange them, there's the same value, right? 7, 7, 8, 8, 2/3, 2/3, whatever. So this goes like this, and like this, and like this. So that is indeed a reflection across the identity function. That's nice. Sort of, if you like graphs. But it does fill in and let you know what's going on. Now, here's the thing that's interesting, to me anyway. And it makes sense too. Notice, remember, for a function to have an inverse, what was the one requirement for it? Has to be a one-to-one function. Remember? Remember one-to-one? That means it passes the horizontal line test. Remember, vertical line test to be a function. The horizontal line test has to have a one-to-one function. And only one-to-one functions can have inverses. Okay? Now here's the other thing. A one-to-one function, if it's a continuous function like this. Now if it's just a few point ordered pairs, you just swap them. That's all you do. But if it's a continuous function like this, a one-to-one function, in order to pass the horizontal line test, it can't back up on itself. So this is a strictly increasing function. It slows down the increase, but it's still increasing, Has to be strictly increasing or strictly decreasing. It can't change directions. Well, guess what? If f is a strictly increasing function, that means f inverse also is a strictly increasing. It doesn't become strictly decreasing. It must also be strictly increasing. And if f was a strictly decreasing function, then f inverse must be a strictly decreasing function. To me, those are harder to graph. Increasing functions, easy for me to see. Decreasing functions, I have to stand on my head and do something. I don't do that well. Okay. And you don't want to see me do it either. Okay. All right. Let's move on. Here's example 3, and they do this one. Sketch the graphs of the inverse functions f of x equal 2x minus 3 and f inverse of 1/2 of x plus 3. If you don't mind, let me back up just a little bit to these two that we just did. Oh, here they are. Let me clear those out of the way. Now, remember when they were real obvious things, adding or subtracting, multiplying and dividing? You notice here you still have the different operations, but which order you do them is not really clear. So this thing by inspection is not really a good idea. This one had in it a division and a subtraction. And sure enough, this one has an addition, but it still has a division in it. Okay? So that's the ones that work. This one, forget that one, not even inverse. So you can't always say you expect to have a multiplication because that had a division. You don't, okay? You do have a subtraction and addition, so you can't just look at it and say, oh, I bet you that you can say it, but I bet you most of the time it's going to be wrong if it has multiple operations in it. Those like that one, really simple. These, not quite as simple. So let's go back to the one we were about to work on. That's what brought it to mind. Okay. This one does have both. The F function has a multiplication and a subtraction, and the F inverse has an addition and a division. So, yeah, it sort of is, but what order do you do them? Not too sure. But they're telling us they are inverse functions of each other. We'll take their word for it, especially since we're going to graph it, and then we're going to show us whether they are or not. So, let's do the graph. Now, I'll do the whole graph and nothing but the graph. Okay. Now, let's tick off a few points. 4, 5, 6, 7, 8, 9. I won't need that many. I never get them spaced evenly. Okay. Okay. Let's see if that will work. F is fairly easy to graph. Tell me how to do it.
I know I'm so bad at girls. It's going to be over.
Okay.
Help me out, class ready. Okay.
What kind of function is F? Hint, the only exponent you see for the variable is 1. What kind of function is that? Linear. Makes a straight line. Okay? What is that form often called? That equation of, simplest equation of a linear function. Has the word slope in it. Slope-intercept form. Y is equal to mx plus b. F of x is y. M would be 2. B would be minus 3. Right? Now, what does that M and B stand for? No clue, huh? Yeah. M is the slope. Now, I had a student ask me one time, where did they get M for slope? I said, I have no idea. And another student in the class happened to say, could it stand for mountain? And of course it doesn't, but goodness, that helps me remember it. So mountains have slopes, so M is the slope. So the slope is, in this one, mx plus b. M would be 2, the coefficient of x. 2. And b, what is b? Yeah, it's -3. And what does that stand for? M stands for slope. 2 is a slope. What is -3? The y-intercept. Perfect. So that means it intersects the y-axis at -3. I just barely got it in there, didn't I? But it has a slope of 2. What does slope of 2 mean? You go up 2 for every one you go over, right? That's what slope means. Rise over run. So up 2 for every one you go over, up 2 for every one you go over, up 2 for every one you go over, something like that. Up 2 for every one. I'm just going to draw it in here, or at least my scaling is not good. It's supposed to be a straight line. I don't draw straight lines too well. Something like that. Someone else here? Good deal.
How you doing? Good to see you.
You're on the right page at the moment, good. Beyond. All right, good deal. Thanks for being here. Okay, we're doing example 3 on top of page 86, or near the top of page 86.
He was just telling us about him and the beat and the slope, stuff that we supposed to, we learned way back when, but it's so far back. Yeah. But he figured it out though. He did it. So -3 was our.
All right.
So, yeah. So we started at -3.
Now, we've got the next one to do, and this is a little messier.
The inverse one?
Yeah. And the reason is because of that beautiful little fraction in it, isn't it? Ooh, yeah. Okay. But it's not written quite in the neatest form either. If we wrote it in a little bit neater form, and you wanted this in a different color so we can distinguish them? What color would you like? Red? Is that what you said? Okay, we'll try red. Ah, we got it first time. So this F inverse is, I'm going to distribute the 1/2. It'd be 1/2 x plus an ugly little 3/2. Okay? And what kind of form is that? What kind of equation is it? Or function is it? Linear function, because the exponent for the x is 1 and only 1. Okay? And what are the things you can pick out of it? That form is called the, what form? We said it last time. Slope-intercept form. And what does each of those words mean? Given that? That's it. Y-intercept is 3/2. Well, 3/2 is 1.5, right? So here is the y-intercept. Always plot the y-intercept. That's a point. Slope's not a point. So it's 1.5 is 3/2. There's where you are. Okay. This time you're going up 1 for every 2 you go to. Yeah, up 1 because the slope is 1/2. Up 1 for every 2 to the right. Okay. Yeah. Now that's a little messy, isn't it? So what I'm going to do, okay, I'm changing that F inverse to y here. Okay, I'm going to multiply both sides by 2 so I can get rid of my fractions. I mean, I like fractions fine, but I just not mess with them if I can help it. So that would be 2 is equal to x plus 3. Okay? No, 2y. I left off my y. 2y is equal to x plus 3. Let's see if we can find any other point on that graph except a fractional point. That's a fine fractional point there. But let's see if we can find another one that's not a fraction. So in other words, give me a y. Since the y is the one confused here, give me a y, any old y. Make up a y. 2, okay? 2 times 2 is 4. So 4 is equal to x plus 3. Let's subtract 3 from both sides, and what do you get? Let's do it. You chose y equal 2. Okay, so this gives you 4 is equal to x plus 3. Now subtract 3 from both sides. So x equal 1. So when x equal 1, y's got to equal 2. So let's plot that one. X equal 1, y equal 2. There we go. I like that point I like the other one okay, but this is a lot easier to go with because now we can do our slope and go up 1 for every 2 to the right. And looky there, we hit right smack on that one. And we do another up 1 for every 2 across, and there's another point, up 1 for every 2. So basically, and we'll go also down 1 for every 2 to the left. That gives you a plus 1/2, 2. Down 1 for every 2 to the left, down 1 for every 2 to the left, down 1, and basically you see what's going on here. So basically you get the straight line, sort of straight line that goes something like that. Okay. Now give me another color.
Green.
Green, okay. I'm going to go with light green this time. Okay. Now our line y equal x. That's what we're doing. We're going to do that one in green.
Okay.
Okay? Give me some points on that one.
Just what numbers?
Yeah, give me a number. Any number. Huh?
3.
3, 3. 1, 2, 3. 1, 2, 3. Hey, there's our point right there. Okay? But also 0, 0, 1, 1, 2, 2, 3, 3. 4, 4, 5, 5, minus 1, minus 1, minus 2, minus... It's the identity function. Okay? X is identically equal to... Oh, I don't want to solid it in. I want to dot this one in. There is your reflection line. And sure enough, the blue line and the red line are reflections across each other. And on that line, that's where x equals 3, y is equal to 3 for both functions. Now, sure enough, when you put a 3 in for x there, you get 2 times 3 is 6, minus 3 is 3. So the y is 3. You put a 3 in for this one, 3 plus 3 is 6, half of 6 is 3. So sure enough, 3, 3 is on both lines, and it's on the reflection line, and sure enough, that's what you got. Those are supposed to be straight lines, by the way, but yeah, we can look at it. Okay. All right, now, let's see how the book did it. I bet you it wasn't quite as pretty as ours. Do you think? Hey, don't answer that question. Okay. Here it is. The graphs of this are shown here. They first graphed y is equal to, or f of x equal to 2x minus 3. There's your y-intercept. It's 0 minus 3. And then you went up 1 for every 2 across. Up 2 for every 1. And up 2 for every 1. Up 2 for every 1. So all these points, when you increase the x by 1, increase the y by 2. So it would be a 1 minus 1. A 2, positive 1. A 3, 3. 4, 5. You go increase the y by 2 every time the x, or decrease. So it'd be a minus 1, minus 5, minus 2, minus 7. You know, they keep on going down here. Okay. The one over there, a little bit more challenging to graph. Now, we found out what the slope and intercept were to begin with. They didn't bother to do that. They just started plotting points. But we also plotted points, if you remember. We got 1, 2. And then we knew, because we knew the slope was 1/2, then you went up 1 for every 2 over. So that became 2 to the right. So that became a 3, 3, 4, 5, 5, 7. You know, you go right. No, I said it backwards. Okay, I'll do it. You go to this. Increase the x by 2, the y by 1. So the next one would be a 5, 4, a 6, 6. No, that's not right. 6, 5. Yeah, you just go up all at once. Okay. Or you go down, okay, and we start at 1, 2, so just go down 1. That would give you, no, down, left 2, negative 1, down 1. That went to 1. Negative 3, 0, negative 4, negative 5, negative 1, negative 7, negative 2, keep on going down.
Okay, so Dr. Fowler.
Yes.
That's the slope formula. So the half is, so you go up.
Yeah, okay.
Fraction, so
Right,
that's
okay,
why you
slope,
do it.
okay, this may or may not be what you're asking. Like I said, you're going, it's rise over run. Ooh, let me go back to black, okay? Or dark anyway, it's not black, okay? The slope is equal to rise over run. Rise being on y, run being on x. Okay? So if you were going, the slope happened to be 1/2 because of 1/2 of x, right? That's the slope. So that means a rise of 1 for a slope for a run of 2. So up 1 on y for every 2, 1 up, okay. Now, going the other way, you're going left on x, so that would be a -1, and you're going down on y, which is a -2, and -1 over -2 is also 1/2. Okay, so that's why you go down it. When you go, if it's a positive slope, when you go left, you have to go down. Okay. If that was a negative slope, when you went right, you would have to go down. When you went left, you'd have to go up. So one's positive, one's negative. Right? And they keep going the right way on both sides. They don't change direction. All right. Is that what you're asking? Yeah, I thought it probably was. Okay. All right, we have just done example 3. I can't think of anything else. It appears that the graphs are reflections of each other across the line. Y is equal to x. And here, when you look at the ordered pairs, you see that's true. This is a -1, 5. There's a -1, -5. Here's a -5, -1. A 0, -3. A -3, 0. A 1, -1. A -1, 1. A 2, 1. A 1, 2. A 3, 3. A 3, 3. That's the same. If you went on the other side, the next one going up this way would have been a 4, 5. If you go this way, you go right 2, that would be 5, and up 1, 4. Yeah, further. All right. You can further verify this reflective property by testing a few points on the graph. I think we just did. Okay. All right, there's example 3. Oh, and they go on. Note that the following, this is what we're just saying. I thought that's what they were all anxious to do. And maybe that's what they meant. Let's check a few, and they did. So on the graph of this one, it was -1, -5. On the inverse, -5, -1. This is 0, -3, -3, 0. 1, -1, -1, 1. 1, 2, 1, 1, 2. 3, 3, 3, 3. Because that's also on the identity function, 3, 3. Okay. Good deal. Now, they're skipping example 4. Shame on them. Oh, and by the way, there's a checkpoint right after example 3. So let's go back and do example 4. Verify graphically that the functions f of x equal x squared and then they put in parentheses for x greater than or equal to 0. Okay. And g of x, and this is the square root of x, and they don't say anything about the x there, or inverse functions of each other. Now, why in the world would they say here, x has to be greater than or equal to 0? You can plug in any x in the world and you'll get a value here. How does that look? How does that plot? Remember, that's one of our parent functions, wasn't it? How does the squaring function look? What's the shape of this graph? Yeah, the squaring function. Listen right here. Parabola, exactly. All right, that's a parabola. Okay, well, why did they say all these x's are functional values? Why did it say x has to be greater than or equal to 0? If we're talking about them being, and here's what we're saying, verify graphically that these two are inverse functions of each other. What's required to be before a function can have an inverse? What must be true about that function? One-to-one function. And what's the test? Horizontal line test. Picture that parabola. Does that pass the horizontal line test? No. The parabola looks like this, right?
Yes.
Horizontal line cuts it twice, not once.
Right.
Wrong. So we have to restrict ourselves to only positive x's. That's why they put that in there. For that to have an inverse, it must be restricted, the domain, to only one side or the other. They chose the right-hand side. Okay. I just want to erase this part. Okay. Now, so verify graphically that these two functions are inverse functions of each other. So since we're restricting ourselves to only positive x's, then I'm going to move the y-axis way over here, okay? But since you're taking those positive numbers and squaring them, guess what those are all going to be? Positive, okay? So we are all in the first quadrant. We don't even mess with any negatives anywhere here. Give me a few points. Oh, let me tick off a few lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, something like that. And up here we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, something like that. Give me a few points. Give me an x. 2. What would be your y? This is F, by the way. We're plotting this in the dark color. Get back here. Okay. Plotting this in the dark color. 4. You got it. 1, 2, 3, 4. So 2, 4. Ooh, right there on the lines, or right below it, right there. Give me another x. 1. What would be its y? Second? 1. Okay. Give me another x. 0. What would be its y? 0. Give me another x. We already did 1 and 2. 3. Okay, and what would that be?
These are 3.
Yeah, so that would be 9. And I tried to get the 9 up here. I probably cheat a little bit. So here's what this one looks like. Something like that. Half of a parabola, because we're only dealing with positive x's. This is 1-to-1, strictly increasing. If you included anything over there, no longer a 1-to-1. Okay? Now, what color you want green G to be? What's that? Pick a color, any color. Second?
Light blue.
Light blue, that one. It's almost a Carolina blue, isn't it? Okay. All right. Now, give me an X. We're doing G now. Give me an X. Second? 0, I like it, okay. What's the Y? 0. Got it. Got that one. Give me another X. 1. What is this? 1 also. Hey, are these the same graphs? I don't think so. Okay, give me another X.
3.
I don't like it. 9. That's a good one. And what's this? Y then? 1, 2, 3, 4, 5, 6, 7, 8, 9. And go up 3. Something about right there. Give me one more. 4. And what's its Y? I like the way you are thinking here. Okay? And what do we have here? We have half of a sleeping parabola, right? Okay? Now give me another color. It is, isn't it? Almost a teal, isn't it? Next. Another color. Well, we only have one purple. Let's do that purple. Okay? All right? And it's going to be the 1-to-1 function. Give me some points on that one. The identity function. These are easy. One's identically equal to the other one. So give me an X. What we're doing now is Y equal X. Give me an X. You can use the same ones. 2. So Y would be 2. And 3, 3. 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 1, 1, 0, 0. Hey, here's what the identity function looks like. It splits right smack down the middle, right? And sure enough, this one is a reflection of that, and vice versa. Right? This one's strictly increasing, that one's strictly increasing. Yep. Everything seems to fit. And these 2 points, 0, 0, and 1, 1, have to be at points of intersection because they're on this one, they're on that one, and they're on the identity function. Perfect. Make sense? All right.
The inverse, she said, what's that identity function?
Oh, the identity function is this one right here, y is equal to x. The two of them are identical to each other. 7, 7, 4 thirds, 4 thirds, negative pi, whatever the first one is, the second one's that same thing. And that's the diagonal line there, but cuts that in two, bisects that angle in two. All right, there was example 4. Okay? Now, we've been talking about it like crazy. The reflective property of the graphs of the inverse functions gives you a geometric test. We've just been doing this for determining whether a function has an inverse function. That test, oh, we've already been talking about this. Did I jump ahead on it? I must have, sorry about that. That test is the horizontal line test for inverse functions. The horizontal line test for inverse function. A function f has an inverse function if and only if no horizontal line intersects the graph of f more than once. Okay? That's the test for the horizontal line. Like a vertical line test, the vertical line can only intersect it once. Horizontal line test. So we've been using it. I'm sorry, I thought we had already done it. Sorry. Okay, if no horizontal line test, I thought we had done this too, intersects the graph of f at more than one point, then no y value is matched with more than one x value. That is an essential characteristic of what we call 1 to 1. Okay, that's my, when I want that answer, that's what I'm going to do. Okay, 1 to 1 function. So 1 to 1 function f is 1 to 1, and each value of the dependent variable corresponds to exactly one value of the independent variable. It's kind of just the reverse of what a function was. Function for each x, you only have one y. Now for every y, you only have one x. That's why it's 1 to 1. There are no duplicates. Okay? Function f has an inverse function if and only if it is 1 to 1. Okay? Those are the two halves of the same coin. Okay, sorry, I was thinking we had already done this. All right. Let's consider this function, f of x equal x squared. I've seen that somewhere before, haven't we? Okay. All right, the table on the left is a value for all the values of f of x equal x squared. Table on the right is the same as the table on the left, but you've swapped the columns. Okay? And this is a function for sure. When x is minus 2, f of x is 4. Minus 1, 1. When you square minus 2, you get 4. Square minus 1, you get 1. Square 0, you get 0. Square 1, you get 1. Square 2, you get 4. Yeah, we got that. It's a function, right? Every x, you get 1 and only one y. Okay? What happens if you flip the values? Now you have a 4 minus 2, a 1 minus 1, a 0, 0, 1, 1, 4, 2, whoops, whoops, whoops. Now this isn't a function. So the inverse, you might say, is not a function because for any x, you get 2 y's. Can't happen. But you could have seen that back here. This is a 1 to 1 because that means for any y, you can only have one x. And this one failed, that one failed, because these two failed. So yeah, this wasn't 1 to 1, so you couldn't have done the inverse. Not allowed. Okay. So how can we fix that? How did we fix it in the last example? You know that the domain to be only positive values. Now that is 1 to 1. You could have done only that, values less than or equal to 0. That would have been 1 to 1. So you can limit your domain and still have a 1 to 1 function. You have to keep in mind that's limited domain. It's not all real numbers anymore. Those straight lines, they're good everywhere. Any one that curves, you got to watch out for. If it curves back on itself, have to exclude those values. Okay? Now, the table on the right, the one we just were looking at here, does not represent a function because for x equal 4, for instance, match with two outputs, minus 2 or plus 2. So f of x equal x squared is not one-to-one and does not have an inverse function over the domain we were just looking at it, over all real numbers. Won't happen. If, however, we limit the domain to just this half or this half, then it is one-to-one. Okay? And those would have inverse functions. Okay. Here's a function. Graph of function f of x. Is this the next one? Yeah, example 5. And by the way, this example 5, you can go to larsonprecalculus.com for an interactive version of this type of example. So if you want to hear more, see what he says about it, you can get a little bit more than the book gives. Okay. Oh. The graph of this function, f of x equal x cubed minus 1, is shown here. First question, is that a one-to-one function? Yes. Every horizontal line only intersects once. It might be a little doubtful here because it looks like it's getting close to flattening out, but it never actually flattens out. It's always slightly increasing and then starts increasing more. So, yep, that's a one-to-one function. Because no horizontal line intersects the graph without at more than one point, it is a one-to-one function. That means it does have an inverse function. Finding that one, though, not going to be something you do by inspection. It's got to be a rule. So that's where we're going to be heading soon. We may not get there today. Let's see. Did I bring my watch up? Huh? 34. Okay. I know the rest of the class will be very disappointed if we don't finish this section today. No.
This was like 2,
Yeah. Good deal.
Or that one-on-one, that's what it is.
Yeah.
It's just 3 of us, so it's in one-on-one. And it's so many, it's like,
Yeah, we're more like a one-to-one function that way. Oh, all right, okay. So here's the B part. Here is a graph of f of x equal x squared minus 1. That doesn't look as complicated as this one does it? Okay. Is that a one-to-one function? What you think? Is that one-to-one? No, the horizontal line test fails right there, you see? It fails everywhere above minus 1. Everywhere it's going to intersect twice. Down here it doesn't intersect at all. There's in fact only one point only intersects one place. The rest of the places it fails. So that's it. Not a one-to-one function. You can't find a horizontal that intersects the graph. You can find a horizontal function line that intersects the graph more than once. It's not one-to-one. Does not have an inverse. Unless, of course, you do what? Limit the domain. The right half or the left half. Those would be one-to-ones, but not the whole function. Not for all real numbers. Okay? And we can do that. It's legal in most states. Okay. All right. Got it? Okay. Is there no?
Don't say yes a lot. When you in class and you say you got it, I'll be like, oh my goodness.
See, part of the problem is with the big class, I can't see everybody who shakes his head. Okay. All right, there is a checkpoint at the bottom of the page. Please remember to do that. Now, remember we said at the very beginning, on really easy functions, you can sometimes guess what the inverse function will be if it has one. Now we know how to check to see if it has one. But for more complicated functions, that inspection thing just isn't going to work very well. You will spend all day long inspecting and may never get it. So here we're going to do it algebraically, which is going to shorten your time of inspection. And We love algebra. Okay.
We lazy.
All right. For relatively simple functions, such as the one in example 1, you can find the inverse function by inspection. That's what I was just saying. For more complicated functions, it's best to use the following guidelines. We're going to get to them in a minute. Now, they say the key step in these guidelines is step 3. There's a lot of key steps. I don't break them down quite the same way they do, so don't worry about the numbering of the steps. But here's the thing. You're interchanging x and y. Isn't that what we first did when we were doing an inverse function? You flip the x and y. So that's why they say it's a key step. That step corresponds to the fact that inverse functions have ordered pairs with the coordinates reversed. So here are the steps. Now, written out, they look or sound a little blah, blah, blahish, okay? When you do them, I hope they'll make more sense, okay? Now, first, decide whether it has an inverse. If you have a function that doesn't have an inverse, don't try finding an inverse. You can't find one, okay? So first, you have to verify it does have an inverse. And what's the test? To tell whether it has an inverse or not. Horizontal line test, of course. But that requires you to graph the function. And I know y'all like graphing, but you know it's not my favorite activity. Okay? It's okay, but it's just not my favorite. So sometimes I'll try to figure out another way to figure it out. Okay? But if nothing else, graph it and then see if horizontal line test works. Okay? So you've got to first make sure it has an inverse. Now, the next step. What was the one thing I told you always in this course, the main thing to remember? What is f of x? What is it? In this course, f of x is just what always another letter. Y, okay.
Oh, why?
I'm trying to do YMCA for you. And it's the Y, okay. Remember, f of x is y. If you remember that, you got most of this course kicked, okay? You got it knocked, okay? So, next step, after you make sure it has an inverse, then just change the f of x to y. That's it. Just to replace the f of x with letter y. Now, that comes to example 3. Once you've done that, then switch your x's and y. Just switch them. Make everywhere you see an x a y, everywhere you see a y, make that an x. Now, I would do this as the number 4. Then solve for y. To me, that's an important step. It needs to be its own step. Once you exchange the roles, then solve for y. Okay? Now, once you solve for y, that y is now not f of x. That's f inverse of x. Once you switch to x and y, then the y becomes f inverse in the new equation. Okay? Then is our favorite step, verify. And that one, you have to do f of f inverse, make sure that comes out being x, and then you do f inverse of f, and make sure that comes out x. That's how we verify. Okay? So, we've done all the steps before. They're pretty easy. We're just putting them together now. Okay? Need them any longer? Okay. All right. So, find the inverse function of this function. F of x is equal to 5 minus 3x over 2. Now, and know what they want us to do, graph it. I really don't want to. I want to argue my way through it, okay? Now, here's what I'm going to do. You tell me if you think this is okay. I'm still in purple. I'll get back to dark, okay? Now, I'm going to split this up and call it 5 halves minus 3x over 2. Is that legal?
In all states?
Yeah, in all states, yes.
I'm just pretty sure.
Okay. What you think?
That's cool. Yeah.
Okay. That is true. Okay. It's sort of like subtracting fractions. Find the least common denominator, then subtract the numerators, keep the denominator. We're just doing it reverse of that. We have a common denominator, and let's split it out. Okay. Now, I'm going to rewrite that slightly, and you tell me if this is legal too. Minus 3/2 x plus 5/2.
That's the inverse.
Huh? No. This is still the same function. All I did was switch flip, just do it in a different order.
Right.
Minus 3/2 x here and the plus 5/2 here. So that's the same, right? And I did pull out the fractional form and left the variable. But that's good too, right? Okay. Now what does that look like here? I know the fraction, but ignore the fraction. What form is this? What kind of function is that? Linear function. Absolutely, because the exponent of your variable is 1. And what can you tell me about that linear function? Should be able to tell me 2 things about it. I'm really only interested in one, but what can you tell me? What form is that? All linear functions can be written in this form, and are written in this form. Slope-intercept form. Now, I really don't care what the intercept is too much. If I was going to graph it, I really care. But I'm not graphing it if I can help it. So this has a slope of minus, no, that's the y-intercept.
That's the slope.
The slope is the minus 3/2 x.
So y-intercept.
3/2, minus 3/2. Yeah, the y-intercept is 5/2. The slope is the mx plus b. M is the slope. Okay. All right. Now, here's how I avoid graphing. Okay. Here's how I avoid graphing. I say this is a line, right? Okay. And it has a negative slope. Guess what? Without doing a single graph, I know that has to be 1-to-1 because it doesn't ever turn back on itself. It's either going downhill this way, uphill that way. Never turns back on itself. Horizontal line test works everywhere. So without doing the graph, I think through it. I say, if I can get this in a linear form, yeah, that has to be a straight line. If it's a straight line with any, now, if that straight line had a 0 slope, wrong. Okay. But if it has a positive slope or negative slope, then it's going to be 1-to-1. So without graphing it, I figured out this is 1-to-1. All right, step 1 done. Okay? So, all right, for me to erase this. Okay, that was all step 1, and we determined, yes, it is a 1-to-1 function, because it's a straight line with slope other than 0. Okay? Negative 3/2, in fact. Okay? So it is a 1-to-1. Step 1 done. What's the next step? Our favorite phrase in the class. What is f of x? F of x with what? Y, exactly. F of x is y. So we just write it down. Y is equal to 5 minus 3x over 2. We'll go back to their form because they like that form, okay? The other thing I did was just to show you that is a linear function. Now, let me also do it this way. That x only has an exponent of 1, and it lives in the numerator. If that x is in the denominator, not a linear function. If it's in the numerator only and has an exponent of 1, it is a linear function. Okay? Guaranteed. So you didn't even have to go through all the steps we did. I was just doing those because we had already talked about slope-intercept form and wanted you to see that. But that is a linear function. The exponent of your variable is 1 and only 1, and it's in the numerator, not in the denominator. So that makes it linear. All right, so there was step 2. We replace f of x with y. That was pretty easy, right? What's the next step? Reverse them, yeah. Right. The x is equal to 5 minus 3 y over 2. We reverse the x's and y's. Okay, remember that was our step 3. They said the important one. See it? Okay, that was pretty easy. Oh, easy so far. Now, the next one is easy, but it just takes a little bit of work. Now and what do we used to do in just algebra class? We would say, solve for y, right? That's what we do, solve for y. Now, that's going to take a few steps here. So it's an easy concept, but it might take a few steps to do. What would be the first thing you do? When they say solve for, it means isolate the y, the new y. Not the old y, that was already isolated. The new y. What's the first thing you need to do to get that y by itself? A naked y there, nothing else around it, okay? So it's the first thing you want to get rid of. What do you like the least? The denominator. How do you get rid of the denominator? Multiply. Multiply this side by 2, but if you do that, you have to be democratic about it and multiply that side by 2 as well, right? Good. Well, that gets rid of the 2. So we got rid of one thing that was complicating the y, in fact, the most complicated part. So let's write down that step again. That's 2x is equal to 5 minus 3y. Yeah, that's already looking better, isn't it? Okay. What's the next thing we want to do? We're trying to isolate the y. What thing is easiest to isolate here? Subtract 5 from both sides. It's furthest away from the y, so let's do that. That's easy. So that gives us what? On the left-hand side? Huh? 2x minus 5, right? The left-hand side. 2x minus 5, right? When you subtract 2 from the left-hand side, that's what you got, right? Is equal to negative 3y. Perfect. Now what? One thing left to do to isolate that y. By negative 3. Divide everything on both sides by negative 3. Okay? I did every term. The book probably is just going to do one, but I think it's easier to... Fewer mistakes this way. Okay? Now, I'll do the left-hand side. That's just y. I'm going to reverse the sides too. Is that okay? We'll go y is equal to... Now, let's take this one first. Now, okay. There's several ways you can write this. Okay? And I'm perfectly happy to keep it sort of in this form. I don't think the book is going to do it, but let's do this. I like this to be negative 2/3 x plus 5/3. Are you okay with that? Yeah, let's take this only has one negative sign, let's bring it out front. And then get the fraction by itself, negative 2/3 times x. And then negative divided by negative is going to be positive, so that's going to be a positive 5/3. Now I like that form because that's my, what form is that?
Linear.
It's a linear function, perfect. What form is it?
Slope.
Slope-intercept form, exactly. That's going to be the easiest thing to graph. Not that we have to graph it, but if we did, that would be easiest to graph. Let me tell you how I think the book will do it, okay? I think they're going to do this like this, and this is the same thing. If we had just divided this side by negative 3, then what we had was y is equal to 2x minus 5 over a negative 3. And that's okay too. That looks a lot like the first function, okay? But I don't really like the way it looks because it has a minus sign. If I were going that far, I'd do one more step. All these are correct answers, by the way, so you don't have to do this. If we negate the numerator, it becomes 5 minus 2x. And if you negate the denominator, it just becomes 3. To me, that's the prettiest looking form. Okay? But it's not really all that useful. That one up there is the most useful form, but it's not that pretty. The one that's in between is what I think the book will do. Now, what we haven't done, I take it because y'all are packing up, that it's getting close to time. In fact, it's past time to go. Okay, but what we haven't done is the second part, which is the verify.
Okay.
The last part. We've done most of it. We haven't verified. I need to find a pencil that works. There we go. Woo, what was that?
Just a water bottle.
Okay. Yeah, I don't know how it, I think I do know how it got here. Okay, someone else teaches in this classroom sometime. Okay, and, ooh, I was looking at the wrong, our example 6 and the one in the book are not the same. Okay, we've done this one well. What we'll go next time is do example 6 from the book, not this one, and that one we will verify. This one we won't bother to verify, but you've just done your first one. Why didn't y'all catch me on that sooner? Okay.
I was wondering, but I was like, well.
Okay. All right. Homework exercises here would be any of the odds 7 through 13. They're all at Calc Chat. 9's at Calc View. Okay. 1.9. They'll all be on the YouTube. You can listen to them.
I saw the test.
Huh?
On the test.
4, 5, 6, 7, 8, and 9.
Yeah, 6. Yeah. Okay.
Mine's active.
Now, the thing is, folks, and this is bad news for you people who weren't here today. The test is not going to be Tuesday; it'll be Thursday because we got
a little more time.
We got 2 examples left to do, and we'll be through with the section.
Okay.
So we will do that. Okay. So I'll just, if y'all want to write them down, I can. Any of the odds 7 through 13, they're all at Calc Chat. 9's at Calc View. Either 15 or 17, they're both at Calc Chat. 15's at Calc View. Do 19. Okay, it's a Calc Chat. Do any of the odds 21 to 31, they're all at Calc Chat. 23's at Calc View. Do 33, it's a Calc Chat. 35's at Calc Chat. Either 37 or 39, they're both at Calc Chat. 41 or 43, they're both at Calc Chat. 41's at Calc View. Any of the odds 45 to 53, they're all at Calc Chat. 45's at Calc View. And then start trying to do well, okay, let's stop there. We'll pick up the rest of those next time. Okay, good deal.
Thank you.
Good deal. Thanks for coming.
Thank you.
If I'd had to talk with an empty room, that would have been the most boring thing ever.